Hello, Maurits here. This will be a short introduction to magnetic fields. We are all familiar with an ordinary bar magnet, and we have two ends. I'm going to call the poles, a north and a south pole. And if we put a small magnet that is movable close to this, we say I put another little magnet there, and the south pole will be attracted by the north pole, so that will put itself something like this. So this could basically be a compass. If I put it somewhere else, like over here, it will be like this, and somewhere there. And if I move this around, it will end up having positions somewhat like this. So I'll change that a bit. If I move it around, it will keep its south pole there, north, south, north, south, north, and so on. And I can move about in different positions, and I can see how it is directed. And if we connect these points, so to speak, if I move it around so it points always along a line, we end up having something like this. This line will now indicate how the small magnet will place itself. And to indicate the direction, I put arrows here from north to south. And this, what I just draw here, is basically an image of how a small test magnet would be directed in this. And this is an image, so to speak, of the magnetic field. So we draw the gravitational field, and previously using arrows and so on, but this is not a way to represent a field. Instead of putting arrows with length corresponding to strength, we instead put lines that indicate the direction. But we don't see the strength now, anyway, from that. Okay, so old time they found out that the magnetic field exists in a sense, or rather they found out the magnetical forces, and the North Pole and South Pole attract, and North Pole repel, South Pole repel, so it's similar to charge. If you take the Earth and have a little compass, we can see that its North Pole points towards the north of the Earth, which means that the north of the Earth is actually the Earth's magnetic South Pole. So you have a magnetic field going from the magnetic North Pole to the magnetic South Pole, something like that, around the Earth. Later on, they discovered that wires conducting electricity also create a magnetic field. And I will now draw a symbol like that, indicating that we have a wire going outwards. So think this is an arrowhead, so the wire is sticking out towards you. Or if I do like this, then the wire, that will be the feathers on the backside of an arrow, so the wire is now going inwards. And if I put a little magnet around, I will notice that it will north, south, and so on. It will point something like that. And we will actually have a magnetic field around the wire that goes around the wire like this. And for this one, it will go around like that. So how do I know the direction, or how do we remember the direction? And one way is to use the right-hand rules. There are several of them, but we will use one of them here. And basically what you do is you put your thumb in the direction of the current, so the current going up for this top one, and your fingers will indicate the direction of the magnetic field. Here the wire is going down, so the field will be twisting around like that. We can also make a coil, or a solenoid, that's also called. We take a wire like this and we make a coil of it, so it goes around like this, underneath this one, and underneath that one, and underneath that one, like this. And if we have current going through that, say current through like this, remember now if I put my thumb in direction of the field, like here, the direction of the current, my field will be curling around like that. And in this case, it will be curling around from the inside of the coil and out. So the field will go something like this, out from the coil and come in from the other side into the coil like that. So that will behave exactly as this magnet. So this will be, if we put an iron bar or something inside this, we will have created an so-called electromagnet. So why do these two behave similarly? Because in reality there is currents going on in here. There could be of several types. You have the electrons spinning around the atom. It's actually not spinning around, but good enough for now. You have also the electrons spinning around their own axis, actually not spinning, but good enough. And all of this generates magnetic fields. Of some material, these will stack up in the same direction, and in the end, it will make the whole magnet create a magnetic field around it. So basically, they behave in the same way internally. Next thing they've noticed is not only that currents can produce magnetic fields, but also that magnetic fields can produce forces on charges, and in the end that means that magnetic fields can create currents. So this is basically some kind of experiment. Someone did it sometime and then they found this out. Suppose you have a magnetic field. Now I will draw the magnetic field. So this is now not a wire, this is indicating a magnetic field, and that magnetic field is pointing outwards. We can also draw that from the side, so we have some kind of magnetic field. And in that field we have a charge, Q, that moves with some velocity v in that direction. So we have a charge, Q, that moves in the field with some velocity. This is seen from above, so to speak, and this is seen from the side. And they noticed that the charge will start to deviate from a straight line, so it must be influenced by some kind of force. And assuming now that the charge is moving perpendicular to the field, they basically found that the force equals to the charge, so proportional to the charge and proportional to the velocity. Bigger charge, bigger force, bigger velocity, bigger force, but also proportional to how strong the magnet were. If you have a stronger magnet field, if you have a strong magnet, you can test that by taking a piece of iron and, oh, this is attracted by stronger force. So they also gave a value to the strength of the field, and we will use the letter B for that. So this is the strength of the magnetic field. We will give it another name later on. So this is basically the formula we have. There's one little problem with this formula, and that is, first, we don't know the direction of the force. The formula doesn't give us the direction, and secondly, it doesn't indicate also if it matters if this is moving perpendicular to the field or not. First rule, how to find out the direction of the force, and we will use another right-hand rule. Previously used the thumb to indicate the current. We will continue to use the thumb to indicate the current. So in this figure, I will put my thumb in the direction of the current. Then I will put my index finger in the direction of the magnetic field. And now I will censor this because the magnetic field is sticking out like that. And my long finger now, the finger, will indicate the force. So we get a force in that direction. So yet again, thumb in the direction of the current is going that direction. We hold your hand in this strange way. You put your index finger in the direction of the field, which is pointing outwards, and I'm trying to twist my arm here some strange way. My long finger will now indicate the direction of the force. So this will be influenced by force in that direction, which means that it will start to curve in its path. And that means that just a moment later on it might be going in a tilted direction against the field. Not in this case, because it will go around there. But suppose we have that the electron, or sorry, not the electron, the charge is moving with some angle. So this is the magnetic field, and we have some angle there. The only part of this motion that is influenced by the magnetic field is the perpendicular part. So we only need this part. In other words, we only need that part. And this is, of course, so if this is the velocity v here, that velocity v times the sine of theta. So we combine that and get the formula force equals to q vb sine theta, and that is the formula that will give us the force acting on the charge. And then we use our right-hand rule to figure out the direction of the force. So if they are tilted something like this, we still have to, so like for example here, these two are 90 degrees. What we use for our thumb is basically the direction of the part of the force that is perpendicular to the field. So in this case, the thumb here will indicate the current. This charge is moving upwards in practice compared to the magnetic field. The field is directed in that direction, which means the force is downward and the electron will start to move in a downward path. Okay, nice. Except for that we haven't talked about what the unit for this is. Of course we can rearrange this formula. So B equals to the force divided by the charge times the velocity, right? That will give us newtons per coulomb per meters per second, or newton seconds per coulomb meter. Not very convenient unit, so we will give it a new unit, and that is the Tesla T. So we measure the magnetic field in Tesla, and the strength of that will be indicated by this. We can test the strength, so to speak, by looking at how a charge is moving. So that is the first short video on magnetic fields. Yeah, you can read it on a book also. That is part 1. Thank you.